Okay, so what is generalization in machine learning? So the goal of machine learning is to have models with high generalization accuracy or low generalization error rather than training performance, right? Because that's the main idea in machine learning. It's all about prediction. And prediction means basically predicting new data points. So we are not that much concerned about the training data. The whole idea of training is that just training, we just use it to fit the model, and then we are not that much concerned about it anymore. That's why the training performance is actually quite irrelevant in machine learning. In generalization performance is basically the prediction of value based on points unseen before, so the test data. Okay. Generalization test error separates machine learning from optimization or curve fitting. If you go back to statistics, right? The idea was about curve fitting. If you remember, for example, linear regression, that means basically, to fit a curve to the data as good as possible. But then there, the focus is on the training data. Here, the focus is on the testing part or the generalization part, right? So basically, we are claiming here that the model is learning something from the data, and then it's doing predictions based on what it learned. But then, how is prediction possible? How is this learning work? What does it mean to learn, basically? So, or let me rephrase that. So, what makes it possible for the model to make accurate predictions on new unseen data? It's basically the question of what makes it possible for machine learning to learn. Okay, so I'm questioning that learning part. Okay, so training and test sets come from the same population. That's what makes it possible for a machine learning model to learn something and then apply it onto new data and then make predictions on that new data. Okay, coming from the same population allows the algorithm to do anything, basically. So in other words, they are drawn from the same probability distribution. But that's why when the algorithm learns from the training data, that knowledge is applicable to testing data. Okay, so if you look at it from the totally opposite way, right, then you can say a random model that does not fit on a training set, or basically it can be fit, but let's say in a totally different data set that's totally irrelevant to what we have, then it will be equally bad in its performance in testing data because it didn't learn anything. Or think of a simple example. Let's say linear regression. Okay, so if you were to assign random values to its parameters, beta 0 plus beta 1, x1, and so on. So let's say you randomly assign beta 0, beta 1, beta 2, and so on, without fitting the model to the actual training data. Then basically you have a random model, and if you were to predict new points either from the training set or testing set, it shouldn't matter because you have a random model, it didn't learn, and it should be equally bad, right? So if you combine these two concepts now, and if you go back to this coming from the same population idea, okay, same population. So now that means if the model were to train on a specific training set, and if you were to get a testing set from a totally different population, then you should not expect the predictions to be good. The model will not be able to do that. Why? Because it was trained on a totally different data set. Think of it this way. Let's say you go to a class, the teacher, after a few weeks, is going to do an exam the following week, next week, let's say. and then all the chapters covered are from the book, let's say between page 1 and 100. And she tells you that you're responsible for the pages between 1 and 100. So you sit down and study. And let's say the whole, class, the book used for the class is 300 pages. And in the exam, the teacher does not ask you questions from pages between 1 and 100, but she asks questions from the topics which are located on pages between 200 and 300. Now, there's a huge gap. The topics are quite different. They are quite advanced. It might be even totally irrelevant. It might be totally new chapters with other topics and whatnot. So basically, you will not succeed unless maybe a few simple questions and maybe simple few things that you had some knowledge from before. So you will basically do quite bad. Let's say out of 100, maybe you'll get 20, 30, maybe even 10, maybe even 0. Okay, so that's the idea here. If you train on a different data set, you will not succeed on the testing data unless the testing data is coming from similar chapters, similar ideas, similar population. Okay. So if that's applicable, meaning both the training and testing set are from the same population, okay, then basically you should expect your model to do good. Okay, and we will talk about the model validation around that, but overall your model should be able to do prediction on the testing data. So when we talk about these data points now, we should mention that these data points, these populations, the data points obtained, okay, sampled from the population, are identical and independent. So they are basically IID, okay, that's what it stands for. That means independent and identically distributed data points. So that in short would mean that there's no correlation, or basically there's no there's no correlation or autocorrelation between the data points. Okay, so one point does not affect the other point of in either positive or negative way. Okay, each point is an entity on its own, and that's another thing in machine learning, at least in the supervised learning algorithms that we are checking here. If there is some kind of autocorrelation, let's say time is affecting the points, and there is some correlation between the points, like when they are sampled one after another. Okay, let's say the possibility, a simple example could be the possibility of red ball coming after a blue ball is, let's say, higher than the average. So basically then, there is correlation between the points. Okay, then that will affect everything. And especially if there is time involved, meaning there is autocorrelation, then you don't have IID data anymore. They are not independent. There is correlation. So then you should account for that. And models like time series and forecasting analysis can be done for those data points. But the normal machine learning models will not do good in them, mostly, at least. Okay, so another thing to so basically these two things, that the points are coming from the same population and they are identical and independently distributed, is like the assumptions that we make before jumping into the machine learning algorithms and before we apply them on the training or testing data. If these things are not valid, you should basically try and see if you can do something about it, or you might go and check some other algorithms models, because machine learning models will not do good on these kind of data. Okay, so what's wrong with training accuracy? Like, why can't we why can't we really apply it? I mean, we can, but it's problematic. So because the main idea here is that the algorithm is trained on the training data. It's basically fit on the training data, so it has already seen those points. Okay, testing on same points will just yield optimistically biased results, so it will be optimistic, right? Because it's like a teacher asking the student the same questions in the exam that they did during the class activities. If the questions are 100% the same, by the number, by the point, then basically you can't really judge whether, assess the student's performance, whether they really learned this stuff or they just sit down and memorized it before the exam. And basically they're doing good in the exam in that sense, and they will just forget it afterwards. So it's the same idea. You should not assess a student's performance based on the same things that you had already done in the past. You can ask similar questions, but the questions should be a little bit different. The numbers should definitely be different, and things like that, just to see that they did not memorize but rather know this stuff. It's the same idea. So you should not assess the model's performance on training data, because it will just be optimistic. So it will be biased, but in a positive way. So you will think that your model is doing better than it actually will be doing if you were to apply it in real world and start getting new unseen data. So the conclusion will not be reliable, okay, based on the training set accuracy. All right, so bias-variance trade-off. So let's continue with this stuff. So there are two main concepts here when you fit a model and you calculate its accuracy based on the validation or the test set. So, well, when I say two, it's basically two extremes. You will be either underfitting or the model is either overfitting. So underfitting is the model is so simple that it cannot capture enough info and will result in a less than desired model, okay? So too simple of a model will result in underfitting. Underfitting will result in large error in both training and testing sets, okay? Because your model is so simple that it can't really learn much, okay? So the key idea here is your model, at least in general, this is the main reason. So it's too simple and it cannot capture the information provided in the dataset. So it learns a very simplistic model, and this simplistic model will basically underfit, meaning both your training and your testing error will be quite high. So what is then the other extreme? It's overfitting. So the model is so complex that it captures too much info. Okay, now we are going to the other extreme. We are doing too much. It even learns from the noise in the data, okay? So, okay, I'm waiting for my mouse to appear. So noise. So there's signal. Okay. Signal. Ever heard of the term signal to noise ratio? So that's what this is. So signal is the data point, basically the actual data points. Okay. And noise is just those artifacts and other stuff that's irrelevant to the actual data. So we are trying to learn from the signal from the data, like those measurements, those different features we have. But when we have too much noise, it can be either in those measurements or it can be just some redundant features, for example, that we are just adding to the data thinking we are doing something good, but we are just adding more and more noise. So then when the model trains more and more, you can think of it that way. And then it basically has finished learning from the signal. There's no more to learn, and then it starts learning from the noise. Okay. So you can also hear things like too many degrees of freedom or parameters. Okay. So again, there's too many features, too many parameters in the model. That's what it makes complex. Or, too many degrees of freedom. So this is a term from statistics. So it means the same thing basically. There are too many parameters. And for example, in this case, parameters are like beta values, right? We go with the linear regression or logistic regression example. If you have, instead of using 2 features, if you use 200 features, you will have 200 and then plus beta 0 parameter. So 201 parameters in total. And probably that might lead to overfitting. Okay, so too many degrees of freedom and parameters. Too complex model will result in overfitting, right? That's what we'll end up with. So overfitting will result in small error in training. So the error training will be small. The training error will be small, but the testing error will be quite large. So that's the result of our overfitting. So we will, and that's again another danger of relying on training error. If we were not calculating validation or testing error, then if we were just to calculate the training error, and if we were to rely on that, we will have actually a very bad model because it might be just overfitting the training data and we would not know about that. Good. So overfitting and underfitting. So if the x-axis is the capacity of the model, and on the y-axis we have the error, the blue line, dashed line, is a training error. So capacity means basically the complexity of the model. You can think of the number of parameters of the model, or just on itself a different model, but which is more capable. So let's say neural networks on the right and a simple linear regression on the left. Okay, so if linear regression is here, probably a deep neural network would be here, for example. So a much more complex model. So your training error will keep decreasing if you have more and more complex model. Because why? Because it will really, stop learning from the signals and start fitting under this noise. So it will even try to capture all those small nuances in the data, if you will. So your training error will keep decreasing. Okay, so you have this line here going. But if you were to have a separate data set, which you use for validation, let's say, and if you were to plot the error of that too, then you would end up with this green curve. Basically, it would decrease for a while and then start increasing. So this point where it stops decreasing and maybe starts to increase, so this change point we can call it. So here it's decreasing, right? And then after this point, it starts to increase. So this is the deflection point, you can call it as well. This is kind of the optimal capacity, so we want to be around here. Even if we can't really find this exact point, we want to be at least in that vicinity there. Because here, overall, the both the training error and the validation are low, and it did not overfit yet. After some point, maybe after some of like this point here, it's increasing the testing error. So that's the point where we start overfitting. Okay, so this place is where there's high overfitting, and this place on the left is where there's high underfitting. Okay, both of these points are not good, so we want to be in the middle. On the left we have a very simple model, which leads to underfitting. On the right we have a very complex model, very sophisticated model, which leads to overfitting. So now tying back this notion of underfitting and overfitting to bias and variance. Okay, this is how it looks like. So when there's high overfitting, that means there's high variance in the model. And when there's underfitting, high underfitting, there's high bias in the model. Okay. I will explain more about bias and variance soon. But basically, this is how we can tie all these ideas, all these notions together. Okay. So another nice figure here is taken from the Introduction to Statistical Learning. Basically shows the relation between different models and how their interpretability changes with flexibility. Okay, as we increase the flexibility, meaning from going from simple model here on the left to all the way to the more sophisticated models on the right, the interpretability, as you can see, decreases. You see, interpretability for simpler models is generally high, meaning they are easier to understand, easier to interpret, easier to explain to other people. But when we go to more complex models, right, the interpretability decreases. Now, when you go towards the right here on this graph, probably the accuracy will increase because these are more complicated models. But the interpretability decreases because you're it becomes more complex. You can't really explain. Sometimes it's even a black box, so you can't really, there's not much to explain. So for example, here you have like models like regression and so on. So you can explain those, right, the beta parameters and whatnot. But when you go to support vector machines, so there's really not much to talk about. It just makes a prediction of -1 and +1. And that's about it. I mean, you can just go the results, go confusion matrix, and that's it. So you can't really explain why it's making that prediction. There's it's a black box model basically. Okay, so for example, you see bagging boosting here, so models like random forest and so on. So if you have decision tree, let's say here, or it's here, right? A decision tree. So it's much more explainable because you've got a tree in front of you, a decision and nodes. Each split has, you can basically explain to the other person, explain to yourself. But when you have many trees coming together, it's not that easy anymore. You can explain a few things still, like the most important feature and whatnot. But, explainability decreases, interpretability decreases. So this graph is a nice way to explain that. So I think, for example, if I were to add neural networks here, they would be even here, down at the bottom. So their accuracy can be quite high, but interpretability can be even worse than these ones. Okay, so this will lead us to parsimonious models, definition of parsimony. So linear models are easy to interpret, however, their accuracy might be lower. So this is the trade-off between parsimony and black box models. Okay, so parsimony being simpler models, black box or more complex models. So parsimony versus complex, we can say it that way as well. So often prefer simpler model, which we call parsimonious models, over more complicated black box models. Okay, so for example, what does that entail? Things like, so what does it mean to have a simpler model, right? Things like fewer parameters or variables. So although regression is generally a simpler and more interpretable model, if you have, I don't know, 100 variables, 100 features, or even let's say 1,000 features, you can't really explain that very well because it's really hard to grasp all those different features, their relation, their parameters. There might be a lot of redundancy, there might be a lot of correlation as well, which is not good for regression. So having fewer parameters or variables will lead to more parsimonious model. Okay, parsimonious models or simple models have another benefit, which is they are faster to train. That's another important benefit there. They are interpretable, we talked about that, and the accuracy might be lower. So this is generally not good, but that's the trade-off. So you either want a very high prediction accuracy or more predictability, more understandability, more interpretability, with less parameters, a simpler model. So it's kind of that trade-off there. Which one do you prefer? Okay. Good, let's continue with this bias variance trade-off. So regression, how does the bias variance trade-off look in regression? So let's say these are the blue points, the actual points. We have the predictor variable here and the output variable here. So if this is X, this is Y, okay? So here our model is this dashed line. You can see clearly it's underfitting. It's a very simple model. It's not really capturing this curvature in this data. So it's not really doing a good job. So both the training error will be high, the validation error will be high as well. When you go to the other extreme, you see how the line is trying to go through each and every single point. How wiggly this looks like. It looks like a snake. So now we are overfitting. Okay, this basically is the idea of fitting to the noise. Okay, because we don't really need to fit through every point. Our goal is to have a good generalization accuracy. Okay, here with training accuracy will be perfect, it will be 0, but the testing accuracy will be quite bad. So we are overfitting here. Something in between of these two extremes is just like this. So it's basically when you look at the data, you see a pattern like this. That's the model that we want to have, because this will generalize much better than any of these two, the new data points. Okay. So if you look at classification, remember classification is not about fitting a line through the points, but more about separating them into separate, different classes as much as possible. So segregation is the idea here, if you want, if you want to name it that way. So how are we doing here in terms of differentiation between the points? When look at this one, the model is just a straight line, simple model. There's quite a few errors here, and definitely when you look at this data, you can do better than that, because overall the pattern looks like this, right? And we see that in the middle. So again, this is not a too complicated model. It's still simple, but it does a much better job. So I would say maybe even just a little curvature model like this could be even better. But again, just this line is also good enough. So this is the optimal one. Overfitting one is trying to get everything correct in the training data. You see the same idea like this. Here instead, it goes like this, this, this. So we have 100% accuracy in training data, but the testing accuracy would be quite bad, I would assume. So this is how it looks like of underfitting or overfitting in classification. Good. So what's the bias and variance relation, or bias-variance trade-off? Okay, that's the more common name. So when the so in general, when bias increases, when variance increases, bias decreases. Okay, and that's what you see here. So bias is increasing. Oops, sorry. Can I delete this? Okay, it's okay. So when the variance is increasing, you see variance is increasing slowly from left to right, right? So this is the model complexity on the x-axis. So variance is increasing as we have more and more complex model. So we are overfitting over here. So this is overfitting area, right? Talked about this before. And here, as that increases, the bias decreases. Okay, bias is decreasing as variance is increasing. So we have here on the left hand is basically when the variance is very small or complexity of the model is very small. So that's where we have underfitting. Okay, so if you go back to this figure here, so this is the left side of that figure and this is the right side. So this is the right side overfitting and this is the left side, for example. Right, this is where we have underfitting. A very simple model. Here we have a very complicated model. So that's the relation between bias and variance overall. When one is increasing, the other will generally decrease. I say generally because we will see some other situation here as well. So again, somewhere in the middle is basically where the optimal model is lying. Okay. So now you see this black curve here as well, the total error. Basically, the definition of error is dependent on the variance and bias terms. That's why it's look like this. So error overall is bias square plus variance. Okay, and that's why you see like a curve like this, an error curve. So when underfitting is happening, the error is large. The model is too simple here. So as we increase the complexity of the model, right? So the bias will start decreasing, the slowly and slowly variance will start increasing. But then towards here we will have an optimal model where the error is at its lowest, and bias and variance are generally low as well. But then if we increase, continue to increase the model complexity, then we will start overfitting, and so variance will increase, bias will decrease, but at a slower rate. So this will cause error to start increase again. You see this error. Now it's increasing again. So and then we will end up with overfitting. So there's a relation between bias and variance. So this is I think we might have seen this. It's a very nice diagram that explains bias variance. So we want to be in this area. This is the perfect model. We have both low bias and low variance. So that will be this in this place in the middle, where we have an optimum model, lowest error possible. When I look at here, for example, we have points together estimations, but they are far away from the optimum desired result. So the bias is high, but since the points are together, so we have a low variance. You can think of this like a dart, you're throwing. So you end up all those here. So your variance is small, but the accuracy is not very good. But when you look at this one here, so you are like scattered around the middle area. So you have overall a low bias because you're close to the actual desired point, which is the red one. But you are scattered quite a lot, so that's why you have high variance here. Okay, so this is the best model. These two can happen. So when you have high variance, low bias, this is overfitting. High bias and low variance, this is underfitting, this one. Now, what about this one? This is the worst case. It's basically both high variance and high bias. And you might think that this might not happen, but basically if you have a super bad model, you know, which does both, which looks both like this, where you have like this kind of behavior, but it doesn't go through the points, it goes somewhere else. Let's say, you know, maybe, I don't know, maybe it was trained randomly. You can think of it that way. I can't really come up with a good example because it's a bit hard. But then you both have a very high variance because it does a lot of weakly behavior there. And it's also not correct. But then you have both high bias and high variance. Okay, and that's the worst you can end up with. All right. So then, okay, we learned about, we are hearing about this bias variance. So I already told you that the error is basically the addition of variance and bias squared. Okay, now let's look at what that means. So this is our target value, the actual target value. We have a function that actually created these points, but then after that actual function created these points, you know, there's this random error coming in, or irreducible error it's also called, with mean 0 and some variance sigma square, or standard deviation sigma value. So basically you can think of this like the nature adding some noise there, if you will. So we can't really do anything about this. That's why it's called irreducible error. Okay, there's nothing we can do really. So now our goal is to predict a function. Okay, so this one. So you see this prediction here, that is as close as possible to this actual function, or this y values. And so remember, that was the definition of error. Okay, so we take the difference, we take the square. The expected value of this is the error definition. So now, again, there's a lot of steps involved here. I'm kind of jumping to the end to show you that this error can be defined with two main terms. So one is this bias here, and the other one is the variance. Okay. So what is bias? Bias is basically that the difference between the predictions and the actual point. You see, these are the predictions, and the expectation of those predictions are taken, and the difference from the actual point is the bias, basically. Okay. And when you have the predictions, so the definition of variance is you have predictions and you have the expected value of those predictions. The difference between these two are the variance. So it's exactly the same as the variance in statistics, right? It's the points. So if you think the expectation is the mean of these points, then it's basically how much the points differ from the mean, right? That was the definition of variance. So that's what it again here is. So this is how far does your, so bias is how far does your predictions lie on average from the actual point, and variance is how much do your predictions differ from the average of the predictions. Okay. And so these terms, bias, squared, variance, and this irreducible error, will basically constitute the error value. So we can't really do much about this, but we can, you know, do our best in our models to decrease bias and variance as much as possible, up to a point. So, and that's where the bias variance trade-off comes in. So the expectation here, okay, this is important, is over the training data. So the average estimator from different training samples. So the idea is here you sample different training points, right? And then you make predictions on them. And so you fit different models basically. And once you fit different models on those different samples, you make predictions, and that's what these are. Okay. Okay, so let's continue with understanding this underfitting, overfitting, and bias variance relation. So so we have y.